don't see it.
Okay, I guess we'll start this morning. Thanks for making it in on this very cold morning. So, some of you have asked me some questions about names, and so I thought I would try to outline an exercise, which is essentially to yeah, it should be. It is. Sure. Yeah, this got this. Oh, sorry. Yes, you're right. And I believe the mic is on, and the volume looks good. Okay, so yeah, so the exercise is essentially to come up with the definition of forcing relation that works inside F. So we gave this definition of forcing relation, which says for every generic filter has this condition, something satisfied. Okay, but that's external because it quantifies over generic filters. And so the exercise is discover the definition of forcing relation by M. Okay, so if I just if this was the only information I gave you about the exercise, then this would be too vague and maybe impossible. So let's do some discussion about what you should do. Okay, so what you should define is you should define a forcing relation, which we're going to call forcing with an S for strong forcing. Okay, and we should read this as strong forcing or forces in the obvious way. Okay, and then that's going to help you define this. Okay, so read this as forces in the obvious way. Okay, and so what are the natural things that you can define in this forces in the obvious way? Well, I claim that actually this is relatively easy to define because this name, remember, this is a set of pairs where one thing is a condition and the other thing is a name. Okay, so forces in the obvious way might mean something like this X literally is one of the things that's paired up with some condition that's weaker than P inside Y. Okay. So just running through atomic formulas. Okay. This is hard to give a definition of. Okay. Because it says something about, these should have the same elements, right? but that's tricky to say. So the natural thing to define for this forces in a strong way is actually not equal to. Because all this has to say is that there's something in one that's not in the other, and forced in a strong way. Okay? So this strong forcing, you're going to restrict your language to not equals instead of equals. Okay? For kind of natural reasons. All right, and then the rest of the things that you need to define are, you know, something like conjunction and something like the existential quantifier, and I guess negation. Okay. And what should you expect out of this? If maybe we'll write it this way. Right, so suppose that you force in a strong way the double negation, right? Then you should expect actually that this doesn't imply that you force in a strong way 5. Right? So if it's, well, how do I want to say this? I mean, this forcing relation, it's acting kind of intuitionistically, okay? And you can read that from this forces in the obvious way. Does this make sense? So if you force in the obvious way, you know, the double negation of something, then it's not at all obvious that you force the thing. Okay? But still this is useful. Okay, the reverse implication is probably true, right? Just on our kind of intuitive reading. The reverse should be okay. Right? And then the theorem you need to prove is that P forces in the regular sense phi, if and only if P forces in the strong sense. Okay, so this forcing relation definitely is going to satisfy this double negation. Okay, and once you prove this, you understand that you can eliminate some double negations, but only if they're on top of them. Okay. Okay, so this is some kind of suggestion about how you should find the definable forcing relation. And it involves digging into exactly what names are and exactly how basic atomic formulas like should be forced. Okay. I assume that Andreas is going to speak up if I say anything crazy. So far, so good.
I'm not complaining now.
Okay, good. Okay, and the thing that I wanted to say is that if you are thinking of trying to understand the name construction, a better way to understand the name construction is through understanding this strong forcing relation first. Okay? Because once you understand this strong forcing relation, you realize that, and you know this theorem, then you understand the sort of arbitrary forcing relation relative to, say, the atomic force over there. Okay, because of this strongly forces the double. Okay. Yeah. Okay, so this is some kind of extended exercise that says discover what you need to do to define the forcing relation inside M, and some kind of extended hint. Okay, and if I sent you the forcing notes, then you have a place to check that what you're is the right thing. Questions about that? All right, so let's define, give a formal definition of iteration, which we did kind of informally last time. And then we'll prove maybe the consistency of Martin's axioms. Okay? We'll at least have like a complete sketch. Okay, so okay. So another thing I should say is that the presentation here comes from a paper of Baumgartner called Iterative. I like this paper better than the sort of standard set theory textbooks for the purposes of this. Although I think maybe Yak even is taking his presentation from this paper. Kunin, I think, does something else. Although I've forgotten exactly what to do. Okay, so we're going to define. So take an ordinal, and we're going to define an alpha stage iteration. Yes, we will. Okay, so there's going to be an inductive definition. Okay, so if we're going to assume in the inductive step that we've defined what it means to be a beta stage iteration for all betas. Okay. So first, I think I need to give some kind of base case. Alpha is 1. Then there is a constant uh, 0 in E, I guess. So that P1 is the set of call P and P1. Right, this is a sequence of length 1. So I guess we have to say something like P0 is 0. And P is below Q if P is 0 is below Q. Okay, so when you lift off the brackets on your sequence, you just get this Q0. Okay, so if at the successor step, if I take my sequences and I cut off the last element, that should be a beta stage iteration that I know the definition for it. I understand because induction, beta stage iteration. And we'll just say that P alpha is isomorphic to P beta star Q beta, where Q beta Q beta okay, and I guess it's not just any old isomorphism, right? This is a collection of alpha sequences. And I guess formally, this is a set of pairs where the first thing is a beta sequence and then the last thing is a name. And so it's again just this isomorphism rearrangement. Okay, so that isomorphism completely specifies the order on this P alpha. It's just the copied order. Okay. I don't need to say anything more in this case. Okay. Okay, yeah. So also, I guess it's worth noting that by induction, we've demanded that this P beta is a beta stage iteration, and inductively that tells me that I know what the ordering is on this P beta, right?
What is that?
So the conditions in an iteration are going to be sequences. Okay, so I guess we've been kind of notating them sort of functionally. And what's going to happen is that because of this, say we have some Q alpha. Okay, what's going to happen is that in order to say that Q is stronger than P, it's going to be some inductive procedure where I fix the common initial segment and the condition down here, which is stronger by induction, needs to force that the next coordinate is also bigger. Okay, and then I continue. So anytime I need to verify that one condition extends another, that involves some working through the inductive definition of the order. Okay, and then limits, right? Beta, which is again this collection of P restricted to beta. P and the alpha is again a beta stage iteration. And if I need to say, okay, a whole list of things. So let's write them out. Okay, so we're going to demand that our iteration has a a largest element where this one R is just the natural sequence of ones. Makes sense. So once we're into the territory of names for posets, then this is an appropriate name for largest element. Okay. Okay, so the next one is a kind of coherence. Okay, so we'd like our set of sequences to be full or to be kind of closed under some reasonable operations. Okay, so what this is saying is if I have beta less than alpha and I have some condition in P alpha, that's an alpha sequence, right? And I have some other condition in the beta sequence for some shorter beta, then I can kind of glue these things together. I can replace the first beta many coordinates of P with Q and keep the rest to be P. And that stays inside my iteration. Okay. This is some kind of very weak closure property of our set of sequences. Okay. Okay, so finally I need to define the order, right? Okay, and so in keeping with this inductive flavor of the definition, when I'm at a limit, P being less than Q means that when I take all possible restrictions, I end up with something that's stronger in that shorter iteration. All right, and I think that that's it.
So in terms of probability, you need the Q is less than P.
I think I'm not demanding that. So the typical thing that happens is that everything up here is forced to be an element of its by the weakest condition. And so if there's no problem with editing this, I mean, this condition here, or this part here, this is just forcing you to include more sequences in your P alpha, right? We set it out at the beginning that it's just P alpha is just some set of alpha sequences, right? And this demand over here is just a demand that your set of alpha sequences is full under this kind of editing procedure. But to your point, these are natural elements of an iteration. When you edit in this way, you do end up with something that's appropriate.
Sorry for shall C sensitive to.
Sure. I mean, it's a definition. So I think I don't know. It is a philosophical point, I guess. Okay, so there's a whole bunch of information here, a whole big long definition, but let's see what you need to specify in order to specify an iteration. Okay? All right, so first obvious thing is that at the successor step, you need to choose these Q betas, right? Okay. And then at limits, you have this condition that for every beta, the restriction becomes a beta stage iteration. Okay, and that P alpha is going to be a set of sequences of limit length. That's just part of the definition. So you just need to say which sequences of limit length am I going to include, right? Which sequences do I include? Okay, and what this second one amounts to is it amounts to this choosing this notion of support. Okay. On which support solution. Okay, so just recall, I think we defined this last time before I gave you this formal definition, but the support of P is the set of betas less than alpha where this P of beta is different from the one. Okay, great. So let's make another exercise, which is what happens when you iterate forcings that are in the ground model. All right, so we're going to specify an iteration by saying that Q beta is always just the Cohen forcing, so just adding a Cohen subset of omega, and the supports are always finite. Okay, so consider finite support. Cohen forcing. Okay. And then what you're going to prove? You're going to prove that it has a dense set, which is isomorphic to the finite support product over the same index. Prove the iteration. Okay, so this is some kind of generalization of maybe an exercise from last time, which is that when you have a two-step iteration and the second step of the iteration is from the ground model, then that has a dense subset that's like a product, or that is isomorphic things. So this is an example for a longer iteration, but it requires that your conditions are in some kind of simple forcing. Just some fixed one. So if the length of the iteration is alpha, then the product is going to be alpha. Okay, and this again, this should get you in touch with the definition of names, right? So everything now in a condition in the iteration is a name for an element of the ground model, right? Because co-enforcing is this set of finite partial functions, and so all those finite partial functions are in. So you have a sequence of names for elements in the ground model, and you need to work with the notion of names and the idea of extension and the iteration to produce this test. Okay. So one more thing I should point out about the this notion of support. So here our conditions are sequences of length alpha, okay? But you could also think of your conditions as partial functions, where they only give information on ordinals in their support. Okay, and those two approaches should be equivalent. Okay, so if you want to think of your iteration not as alpha sequences, but as sequences of partial functions, that might be useful for some type of reason. You can do that. Okay, so there's maybe one more basic thing I should say before we get to the iteration. If you take a generic and you restrict all of the elements that are generic, this is does somebody want to look at the conditions that we used in the definition of iteration and tell me how to prove this?
The dense subset, but you just append everything to make it a dense subset.
And why is that okay? Which of our conditions allows us to append things?
The B.
Yeah, this is part 3, this limit case B. Right? So you're given a dense set in P beta, and you need to produce a dense set in P alpha, right? And you do that by just appending anything. You're allowed to append anything. It's B, and you can check that that forms a dense set, and that when P alpha meets that dense set, and the restriction meets the restriction. Okay. So use 3B. Okay. So in this, this should be what we hoped, right? When we're defining an iteration, we're supposed to be sort of forcing more and more, right? So a generic for a longer piece of our iteration should generate a generic for a shorter bit of our iteration. Okay, in fact, this restriction map, it should probably be a projection in the sense that we defined last time. I think, yeah, that's probably fine. So I think you can check again using this 3B that the map that takes P to its restriction to beta is a projection in the sense that we defined last time. Okay, so okay, so now we're going to prove that finite support iterations of CCC forcing CCC. All right, so again, this is an inductive proof, and we're going to leave the successor step as an exercise. Okay, so for the successor step, we can prove that, right, forgetting the notation above, if I have P star Q as CCC, this is actually if and only if P is CCC and it's forced by P that Q is CCC. Okay, so at the inductive step of your iteration at some successor step, induction will tell you that the iteration so far is CCC. This is part of the assumption of the theorem. The next step is forced to be CCC. And so using this fact, you can conclude that the iteration is CCC. Or that it's P alpha plus 1 is CCC. Okay, but actually it turns out that the converse is true too. Okay, that if you have a two-step iteration that's CCC, it's because the first thing was CCC and the was forced by first thing second CCC. It's a curious thing and possibly important for some contexts that I'm pretty sure that this equivalence fails if you replace CCC with some strengthening of CCC. So if you've heard of like the master property, something like that, then probably that's one of these conditions where the think about which direction might fail. It's probably this reverse one. That the iteration can turn out to have some strong chain condition property without the steps.
I think PC and Q master implies that P not Q C.
Yes, that's correct. Okay, but something funnier happens in iterations. I'm struggling to remember a good example of that right now, so I'll keep it in the back of my mind, see if I can take something out. Okay, but that's the successor step. So we'll make this an exercise. Okay, so this is again a good exercise in working with anti-chains and names for anti-chains. Okay, so we'll go to the limit step. Okay, and there are going to be some cases. In case one, let's take the cofinality of alpha as omega. Okay. So I think a few first of these cases are going to be not too hard. Okay, so suppose that A contained the alpha is an uncountable anti-chain. Okay, but the supports are finite, right? So each condition in the anti-chain has a bound on its support. And that must mean that uncountably often you repeat the same bound on the support. Okay, so there is B contained in A uncountable, and beta less than alpha. And beta less than alpha, so that if E and B, then the support of this P contained beta. Right, all the supports are finite, and so you can fix a bound because of this cofinality omega assumption. Okay, but then this collection of P restricted to beta for P and B is an uncountable anti-chain in P beta. Okay, contradicting our induction assumption. Right, the induction hypothesis is that P beta is CCC. Okay. So case two, Okay, so if the cofinality of your alpha is large, then a kind of similar phenomenon is going to happen. What happens this time? Maybe you guys can tell me what happens this time. So the supports have the same kind of bounded thing, right? For each condition, the support is bounded.
Well, for the chain size from one.
Yeah. Then I can just take the soup over all of the bounds on the supports, right? 5 to make 1. Good. Then the soup of the set of supports P too many things. All of this is less than help, right? Okay, so same contradiction. Okay, so the action has to be alpha has cofinality in X. Okay, so suppose that A is the collection of some P gammas for gamma less than -1. So we're actually going to need to write them this time. And alpha gamma less than -1 is increasing continuous and cofinal. Okay, so that's the cofinality of -1 assumption. Okay, so let's define f of some gamma to be the least delta so that support of P gamma restricted to its alpha gamma is contained in see if I said that right. Okay, I think that's correct. All right, so what are we going to do? We're going to define a regressive function on -1, on limit order, let's say. Okay. So when gamma's limit, alpha gamma is also limit. Okay. And that means that when I restrict P gamma to this limit ordinal, its support is bounded in that limit ordinal. So it has to be covered by some alpha delta where delta is less. Right? So this is a regressive function on limit. is regressive on the okay, hence constant on the stationary set. So let's let S be like one stationary. Be some fixed ordinal. What did I decide to call it? No, sorry, I guess. Right, so our function is constant on a stationary set. And we're almost good. We're almost ready to get our contradiction. All right, so maybe a picture is. So here's a picture. I guess this is really a picture of alpha. Okay, and down here is alpha delta star. And here's some alpha gamma, where gamma is in S. Okay, so where is the support of P gamma? That's what we want to answer, right? The definition of the function tells me that everything in the support of P gamma that's below this alpha gamma is actually way, way down here, right? So there's actually nothing in this interval. Okay, so this, we can think of this as the support of this P gamma restricted to alpha gamma. It's way, way down here. And then probably the sort of rest, right? This is the rest of the support. Applies. Okay. So there are lots of gammas in this test, uncountably many gammas in this test, right? And so if I've chosen, one of these P gammas, if I go along for long enough, then I can find some alpha gamma prime up here, which is completely above the support of this previous alpha gamma, right? And so if I look at its support, then its support has nothing in this much longer interval, right? So can't interact here. Okay. But it may still have, there may still be some problems down here, right? We can't control what's happening with the restriction of the support. Okay, but the fact that if you wait for long enough, the supports up here are going to be disjoint, that's helpful. Okay. So what are we going to use this? We're going to use this to find T contained in S. If gamma and gamma prime are from T, then what do I want? I want that this alpha gamma prime is bigger than the maximum of the support of P gamma. Right. But if you think about it, this actually amounts to intersecting S with some club. Right, there's going to be a club that's closed under this. Take the maximum support. Okay, and this is supposed to be uncountable, right? All right, so we're about ready to get our contradiction. Okay, so we can find using deduction. And find gamma less than gamma prime in T, so that this P gamma restricted to this star, I guess, is compatible with P gamma. Right, so what we ended up with a bunch of conditions indexed by this T. And because I have uncountably many, I can look at all of their restrictions to this ordinal. And that can't be an uncountable anti-chain. That's the induction hypothesis. So there must be two of them which are compatible. Okay. But then the claim that's a contradiction is that actually this P gamma and P gamma prime are compatible. And okay, and it's precisely because of this picture. So here, this is the rest of the support. The okay, so the fact that there are restrictions to this alpha delta star are compatible means I can take some condition that's below both of them up to here. Then when I add the stuff in the support of P gamma up to this alpha gamma prime, that's also an extension. Okay, and then when I add the rest, that's a further extension now to the whole. The whole length of the bus. Okay, so this. Okay, but remember that to see that these guys are compatible by the obvious kind of gluing together, that's an inductive argument, right? Anytime you need to check something about an iteration, you need to go through the coordinates of the iteration to see the appropriate thing that supports every step. Okay. And the crucial thing for that is the disjointness of the supports. Okay, cool. So that's finite support iterations of CCC forcings or CCC. I think we're ready. You can at least give a sketch of the consistency of artifacts.
Sorry, why did you separate the second case from the third case?
Second case from the third case. It's because the third case is the one that requires the work, right? When the iteration is quite long, then essentially new anti-chains of size alpha-1 can't show up at that limit.
But
They must show up at some earlier.
But your proof case 3 works for any uncountable finality.
Just
I mean, probably for some silly reason, right? But that means that I probably have to be a little bit more careful about actually defining my regressive function, right? Because my sequence now is potentially longer.
But the problem
I
is
guess that's probably fine.
that blocks. You can find this like disjoint blocks after that alpha gamma.
and you can, I mean, you basically prove the delta system,
Yeah, that's right. So
and it works for any.
yeah, so this step here is essentially proving that the supports can form a delta system. So the regressive function, it becomes constant, and then this jointifying the tails of the system. That's right. So a good thing to point out is that this iteration theorem is it's just the first of many much more complicated iteration theorems. So you might like to prove that your iteration preserves some much more complicated properties of CCC. In this case, with finite support is very basic. A much more complicated example would be like countable support iterations of proper forcing. For example, this is much more complicated. You can also take this argument here and you can lift it up to higher cardinals, like longer iterations, and then also weakenings of this CCC. So there's a notion of kappa chain condition, which is antichain of size less than kappa. And then here we had finite support, which meant we took a direct limit at all of the limit stages, but for this argument, we only need to take that direct limit like stationarily often. Okay, because this regressive function just needs to be defined on a stationary set. So there are all kinds of refinements of this theorem explicitly, but then also other more complicated theorems where you want to prove something about some weakening of CCC. Like, for example, properties. Okay, so more questions? Let me just give an overview of the consistency of Martin's axiom. Actually, we haven't stated what Martin's axiom is, so let's do that first. Okay, so Martin's axiom. Let's call this Martin's axiom of Aleph-1. This is the assertion that for every so we see coset and every sequence P alpha less than omega 1 then sets P, there is a filter F containing P so that F meets all of the dense sets. Okay, so why is this a useful axiom? This is sort of crystallizing for you consequences of forcing with CCC posets, right? It says that you don't have generic filters sort of in the ground model, but you have sort of partially generic filters in the ground model, at least for sequences of omega-1 many dense. Okay, so it's an exercise to prove that MA1 is equivalent to MA1 for posets of size less than 2. Okay, so what do you need to do? You essentially need to take an elementary substructure. You have your poset and you have your list of dense sets. And if you take an elementary substructure, size less than continuum, and you meet it using the restricted principle, then the elementarity tells you that that filter is good enough for larger poset. Okay, why did we need this exercise? Because the consistency of Martin's axiom is going to go by iterating CCC posets. Okay, but we don't want to have to deal with forcing with arbitrarily large CCC posets. We just want to force with posets of size less than continuum. That sort of bounds how many posets we have to go over in order to achieve this principle. Okay, so the claim, I suppose, CH holds, and P is a CCC forcing size -1, then actually it's forced by this P that CH. Okay, so what do you need to do? You need to understand subsets of omega in the generic extension. So that means you need to understand names for subsets of omega in the ground model. Okay, and it turns out that there are, in this CCC forcing at size Aleph1, there are just continuum many names for ground model continuum many names for subsets of omega-1, and so you can increase the continuum. All right. So how much?
Could I ask a question about the exercise?
Yes.
I can't quite see on Zoom whether that bit is strictly less than continuum or less or equal continuum.
I think I wrote strictly less than continuum. Is that okay?
Well, let's see. Then CH would imply that you've got MA kappa just for countable posets, which you have anyway. So what I was expecting was less than or equal Aleph1. Sorry, less or equal kappa. Sorry, still didn't say what I meant.
Yeah.
Strictly less than kappa, I think, is what you really want.
But in the
It doesn't make much difference because any bound will do.
Yes. So in this formulation of MA, I've just formulated MA Aleph1. I haven't formulated MA, where there's a parameter that's this.
So MA Aleph1. I think you want you want to include posets of size Aleph1 here.
Yeah, sure. So I think that probably Aleph1, the size of most Aleph1 is.
Yeah, less or equal Aleph1 is I think you're right.
Right, because the thing that you want to take a substructure of, it's going to have predicates for all of the dense sets. So there's no way to take an elementary substructure that's smaller than itself. So that seems fine to me. Yeah, good. Okay, so that's actually a helpful refinement. So what we're going to do is we're going to define CCC, sorry, finite supported iteration. CCC posets of length omega 2. Okay, and it's going to be true that at every step below omega 2, CH is preserved by this claim. So the iteration so far is going to be a CCC forcing of size aleph 1 because it's an iteration up to some ordinal less than omega 2. Okay, and I guess I should say that at each successor step, we're going to pick a CCC forcing of size aleph 1 to do. Right? So finite supported iteration of CCC posets of length omega 2. Which at this late stage in the day, we'll just say which goes over all CCC posets of size omega 1. As much as possible. Okay, so the construction of the iteration, the thing that you have to, final thing you need to do is you need to specify what the Q betas are, right? You need to specify what you're going to force with at every step. And so the right thing to do is to build in a bunch of redundancy. So every intermediate model up to the iteration up to some beta is going to have some enumeration of CCC posets of size aleph 1. And you're going to arrange your iterations so that you just keep forcing with those as many times as possible. Okay, and there's some kind of bookkeeping function which allows you to do that. Okay, and that's it. Okay, so this iteration is going to force MA aleph 1, and it's going to force the continuum is omega 2. Okay, and why does it force MA aleph 1? You go to the end, right, and you pick a CCC poset of size aleph 1, right? And by some analysis of names, that CCC poset has to show up at some initial segment of the iteration. And you know that it was it's CCC at the end, right? So it actually sort of keeps its CCC-ness all the way through the iteration, which means that you have many chances for it to come up as the Q beta and force with it. Okay, so if you just force with that poset at some late enough stage in the iteration, then you get this generic filter which meets all of the dense set. Okay, so that seems like a good place to stop for today. We can, I think next time we'll do some consequences of Martin's axiom, because this is another good way to get in touch with what kinds of forcings are out there. And also it allows us to do some things which the force is supposed to do out, which is applications. Set theory 2 analysis. Yeah, algebra. Probably we'll get to Whitehead's problem at some point, but maybe in the third of this. Cool.
Are you assuming that the ground model satisfies CH?
Yeah, the ground model should satisfy CH. Absolutely, right? Because we want to use this claim that as we go along through the iteration, CH is preserved.
Doesn't it need 2 aleph 1 instead? or something like that. I'm not sure why the omega 2 is
Mhm.
Um,